Welcome to Introduction to Quantum Field Theory, not 17, but 18 on free spinor fields. In this video, I will cover the derivation of the Dirac equation from the Dirac-Lagrangian density, and we will talk a little bit about what Dirac spinors, like what a Dirac spinor is, what a Dirac spinor product is, and then we'll talk a little bit about what the Clifford algebra relations are for the gamma matrices. So just like the Klein-Gordon Lagrangian density, there is a Lagrangian density for free spinor fields, and that is the Dirac Lagrangian density. So it's written like this, and there is an adjoint Dirac spinor, imaginary number, gamma mu, partial mu minus m, and then a Dirac spinor again. So what's this weird adjoint Dirac spinor that or conjugate Dirac spinor, adjoint Dirac spinor, whatever you want to call it, this Dirac spinor with a little bar above it? Well, this is actually what's called the conjugate Dirac spinor. So this, which is defined as the Dirac spinor, the Hermitian conjugate of the Dirac spinor times the zeroth gamma matrix. So this is the conjugate Dirac spinor. Dirac spinor. And note that these gamma mu matrices are the Dirac gamma matrices, which you might recognize as the reciprocal basis of the space-time algebra. But note that we're really in the Dirac algebra, not the space-time algebra. So for note, this is the STA is this, and then the Dirac algebra, the STA is G1, 3, and the Dirac algebra is the complex numbers tensor G1, 3, which is, for all intents and purposes, the real geometric algebra G2, 3. So we are actually working in this algebra, the Dirac algebra here. The STA does not have complex numbers. And we're also technically working in the Dirac algebra without considering it as a geometric algebra, i.e. these gammas are matrices, not vectors in the traditional quantum field theory approach. So the spinor product, the Dirac spinor product, the Dirac spinor product is, so you have a Dirac spinor, a conjugate Dirac spinor times a Dirac spinor, which is equal to the Dirac spinor, what do you call it? The complex Hermitian conjugate. I was having a brain fart there. Hermitian conjugate, gamma naught, and then psi, which is the same as saying like if we have two spinors. So a Dirac spinor, right, is two spinors. You have a left chiral spinor and a right chiral spinor, the Hermitian conjugate of that. And then we'll see later, but the definition of gamma naught is actually this 4x4 matrix. So notice that I'm putting a 2 next to these identities, and that's because these are 2x2 identity matrices, and these are 2x2 zero matrices. So this is actually a 4x4 matrix, And because each spinner has two components, this is actually a two component or a four component spinner. Alpha, beta, which is equal to, you end up with alpha dagger, beta dagger, these are technically matrices themselves. So you have to carry the Hermitian conjugate through. Then it's just this. And let's make this a little more even. And then here we're going to expand this multiplication. It preserves the row vector, and we end up with beta dagger, alpha dagger, then alpha, beta, and then when we expand this out, we get beta, alpha, plus alpha, dagger, beta. And so this is the left vial spinner product, and this is the right vial spinner product. So you can see that when you take the spinner product of a full Dirac spinner, you get the spinner products of the left and right-handed spinners, respectively. Now that we're a little more used to seeing the gamma mu, um, or hang on. So we're used to using these gamma mu's for geometric algebras, but we're not used to seeing them as matrices. And as this is not a geometric algebra series, we will be talking about them as 4x4 complex matrices. So what are they? Well, we already saw what this one is. Also, why is there a negative sign there? That was weird. Oh, that's I didn't notice that. I didn't move this there. Okay. Um, so the gamma mu or gamma naught is defined as being equal to the lower or the contravariant and covariant are the same, and they are the matrices 0, 1, 2, and then 1, 2, 0. And these are really 4x4 matrices, so it'd be 0, 0, 0, 0, and then 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0. So this notation means this, and this is just a shorthand telling you that you have a 2x2 zero matrix here, a 2x2 identity matrix here, 2x2 identity matrix here, and then zeros here. So that's the definition. And the definition for the gamma, so all the rest of them, the gamma j, these are actually negative gamma sub j, and these are defined with zeros, zeros, then the Pauli matrix here. And now let's give an example of this. Let's consider the gamma matrix in um, the y direction, which we're actually just going to write with 2. So that's negative gamma 2, and that is uh, did I get a sign messed up here? Hmm, I think give me 1 second to look at some of the math I did earlier. I need to make sure that I wasn't. Yes, I did get a sign messed up. the negative sign is here. So the, the gamma 2 matrix here, all zeros here. And then you have negative I, negative I, and this would be your gamma matrix for the y direction. Because this individual matrix right here, these are your Pauli matrices. So this is how you define all the other vectors from it. Another important one to know, uh, another important one to know. So I'll move this over here, remove this under here. But another important one to know is the gamma 5 matrix, which is equal to gamma 5, and that is going to be defined as negative negative 1, 2, and then positive 1, 2, which in its long form is negative 1, negative 1, 1, 1, all zeros there. And this is the matrix for the gamma 5 matrix. This will come up when we discuss chirality later. And it's a pretty important matrix to know. So these are the definitions of the gamma matrices for the Clifford algebra. Now satisfy these satisfy the Clifford algebra relations. Namely that the anti-commutator of gamma mu and gamma nu, which is equal to gamma mu, gamma nu, plus gamma nu, gamma mu, is equal to 2 times the Minkowski metric, and then times the 4-dimensional identity matrix. Now, you might recognize this as the defining definition of a geometric algebra, and that's exactly what it would be. So, like in geometric algebra, we have the definition that uh, g mu dotted with g nu, which is equal to 1/2 gamma mu gamma nu plus gamma nu gamma mu. And we have that this is equal to the Minkowski metric. This is actually the definition in geometric algebra. So you can see that this is just a geometric algebra in disguise because you have this. But something interesting that I don't know why it's ever presented like this, but we have 4 generating vectors technically, but then you have a 5th one, and they write the Clifford algebra relations for the Dirac algebra as this, but technically this actually generates uh, technically Kali technically this generates um, the spacetime algebra Q13, not the Dirac algebra. So not G23, the Dirac algebra. So why is it that people don't use the correct generators for G23? And I think it's because of kind of like history, like people traditionally generated this and then introduced this later um, by defining this as basically just uh, like the imaginary number times or like, so typically this would be defined as like the imaginary unit define or times gamma 0, 1, 2, 3. But in reality, what this is like logically there might be a sign difference here. I'm not accounting for signs, but like it's logically equivalent to having gamma 5 as a vector. And so people typically introduce it here, but no one ever actually realizes that it's actually a vector. So this is something that I'm just going to present for the sake of rigor, but no one in the field uses this. I don't know why, because I feel like it's a pretty big error to miss this, but the real or the actual relations for the Dirac algebra G to 3 are given by this gamma, basically it's the same relationship, but you can gamma mu gamma nu, but instead of being equal to the Minkowski metric, it's equal. So if mu equals nu and they are less than 4, then this is equal to the Minkowski metric. But then you get an extra +1 if mu equals nu and it's greater than 4. And this would be the relations for the full Dirac algebra, but no one actually presents them like this. Okay, but moving on now from the Dirac algebra, or here, hang on. It would be this be it would be I was in what do you call it? Geometric algebra mode where we don't have matrices. So let me write what this actually would be. It's like this. Okay, yeah, there we go. That's correct. But now that we've written this, let's move on to deriving the Dirac equation using the Lagrangian density. So we're going to do the same thing as we did for the Klein-Gordon equation, and that is to write down the Euler-Lagrange equation, and we take the derivative with respect to the Dirac adjoint, or the conjugate Dirac spinor, because if we take it with respect to the actual Dirac spinor, then we get what's called the conjugate Dirac's equation. But we don't care about the conjugate Dirac equation. We're just going to look at the traditional one. And the derivation here, luckily, is much more simple than the Klein-Gordon derivation. Okay, and then I'm going to do the derivative. I'm just going to write shorthand again of, then I'm going to go up here and go up here, steal this, put that there, then minus d mu of, and then doing shorthand again, d mu this, and now let us take the derivative here. The conjugate spinor only shows up here, and so this is going to just be give us this whole result. So we just get I gamma mu partial mu minus m times the Dirac spinor, and then this right here. Well, actually, nowhere in this equation is there a d mu uh, a conjugate spinor. So this whole thing goes to 0. And so this is the Dirac equation right here. It's almost a trivial derivation, honestly, compared to the Klein-Gordon equation. But this right here, this is the Dirac equation. And this is what we will be investigating a little bit of over the next few videos.